In this video lecture, I will introduce the topic of post-selection inference. There is a big debate going through academia, focusing on p-values, although it's much broader about statistics, and the usefulness of such measures. The problem is actually very wide, and it comes mostly from the fact that many empirical studies done in academia turn out to be very poorly reproducible. So people have reported findings in all sorts of fields. It's particularly in social sciences, but it goes much beyond. And when people replicate those experiments, they do not find the same outcomes. And based on that, a lot of debate has started, and part of this debate is focusing on p-values and the measures of uncertainty, or maybe you should say certainty, reported in particular academic papers. And it got so far that even the American Statistical Association, where essentially most of the big American statisticians are all collected, had to get involved and issue statements about this. So you can find the links to this on Canvas. But let me focus on one of the statements that it has about p-values. So the problem is that p-values are then by opponents said that they are not useful. Well, the American Statistical Association says they are useful, but we should use them and report them properly. In particular, what they are saying is one of their principles, principle number 4, proper inference requires full reporting and transparency. P-values should not be reported selectively. And one thing that for us is very important says conducting multiple analyses of the data and only reporting those with certain p-values, maybe the ones that you actually want to find to be significant, means that all the reported p-values are uninterpretable. So what should we not do? We should not cherry pick promising findings. We should not data dredge, chase for significance, or do p-hacking. If you would do that, then you get the spurious excess of statistically significant results, which indeed seems to be part of the replicability problem. So what we should do instead is look at the whole analysis of what was conducted. Now, of course, this is a very broad statement, and I think it's a very true statement. And indeed, a lot of problems arise with transparency about which analyses were conducted and so on. But I want to use this statement to introduce a property of what we call post-selection inference, and which is something which in high dimensions is very relevant for all of us, because it's something we always essentially do. We're always doing a lot of initial analyses and then only doing inference on our final model, if you want. So clearly, what you can imagine is if you would do this maliciously, then you can indeed only report those p-values, or I mean the same goes for any other measure of uncertainty, so also for confidence intervals, those that actually confirm what you wanted to prove. And this may be part of the problems in science regarding p-values and statistical inference in general. And part of the problem also comes from journals. Many journals would have, again, in particular in social sciences, would have the tendency to also only report p-values or general statistical significance below a certain threshold, often 5%. So if you would do an experiment and you would not find something significant at 5%, you would not get your paper published. Obviously, that provides very wrong incentives for dealing with p-values. Now, this is a very broad discussion. I would be happy to discuss these things further, but let me focus on the things that for us in the course matter most here. One thing relates to multiple hypothesis testing. So if you do enough tests, you will always reject some purely by chance. I mean, of course, that's what we know, right? We do a test with a certain, say, a 5% significance level, then we know that there's a 5% probability that we would reject even if actually the null hypothesis is true. So doing many tests means you will always get some purely by chance, and it would not be contrary at all to the null hypothesis being true. This will be covered in the tutorial. Now the other part that I want to focus on, is, as I mentioned, is the preliminary analysis part. The fact that we do model selections. Now, what we've seen in the Lasso part of the course was that essentially Lasso provided a way to do model selection. We had many possible regressors, and the Lasso, or one of its variants, delivered us a model with only a few of those actually included. So what the ASA is saying in the statement is, well, you should not just ignore model selection, and you should tell your audience actually where you're coming from and what model selection you've been doing. But we also have seen the oracle property, which told us the exact opposite, because the oracle property told us the Lasso is so good that it does as well as if you would know from the start what your relevant variables are. So the oracle property tells us essentially, in the case of the Lasso, you can ignore this statement and you can just report your inference as if you started off with your final model. So clearly these two are contradicting each other. So when it's time to start investigating this more deeply. Now in general, there's a name for the kind of inference that we are doing here, and that is what we call post-selection or post-model selection inference. So it's inference on a model that has been selected from the data. And this in fact already invalidates standard p-values or in general standard inference. Because the model is not fixed anymore. The model is random because the data, which are random, are going to decide which model is selected. But that is not what we've been taught in our basic statistics class when we started doing inference. There we said, well, you have a fixed model, you have a regression on variables A, B, and C, and based on that we could construct confidence intervals or p-values for tests. Now the oracle property tells us, this randomness of the model is not a problem, because we do so well that actually if we have enough data, enough observations, then the model is going to converge to the true model, so it's not going to be random anymore. We can treat it as if it were known. Now let's have a look at a small Monte Carlo simulation study to show that this is actually not such a good approximation of reality. So what I'm going to do is I'm going to take a simple linear DGP where I have p variables, and I'm going to assume that the first two are relevant, so I take coefficients just 2 and 1, and everything up from 4 and higher is irrelevant, so has a coefficient of 0, and I'm going to play with my beta 3. So beta 1 and 2 are relevant, beta 3 is, I'm going to vary that, and beta 4 up to p is going to be irrelevant. I'm just going to take a very simple process. I'm going to generate everything as normal, and for the axis I want to have a certain correlation rho between the variables in x. I'm going to take something which is not very high dimensional, in fact it's fairly standard, 50 observations and 10 variables. I'm going to increase that to 20 to have a bit more high dimensionality here. And I'm going to take particular elements in my beta factor, and I'm going to construct confidence intervals for those, 95% confidence intervals for those betas. And then I'm going to do that 100 times, and every time I'm going to check if my interval that I constructed actually covers my true parameter. So this is a very simple Monte Carlo evaluation of standard confidence intervals in the linear regression model. Well, so far so good, you would say. This all seems very standard. Now, what I'm going to do is evaluate how the method that I use to actually do this estimation and then intervals, how those are going to actually perform. So what I'm going to do first is I'm going to do the lasso or similar methods to select relevant variables. So I'm going to choose which out of these p variables are going to be relevant, and I'm going to do inference on beta 3, so the one that I vary, the coefficient that I vary. And the way I'm going to do that is the oracle property. So I take the lasso, and then I might have the situation where beta 3 is not included. So I might have the situation where my coefficient is set to 0. Well, if that's the case, I'm going to, again, the oracle tells me, these irrelevant variables, you can delete them with correctly delete them with probability up to go up to 1. So I'm going to say, if this is the case, with certainty I say beta 3 is 0. If beta 3 ends up in my model, so I get an estimate which is not equal to 0, then what I'm going to do is I'm going to, again, using the oracle property, say focus on only the selected variables, and then just slap an OLS confidence interval on that. So I'm going to do my estimate minus the standard error times the cutoff points from the normal distribution, and on the positive side plus the standard error times the cutoff point. And the standard error I'm just going to calculate in the least squares way, using only the active set of variables, only the selected variables in S. And the oracle tells me that I can do this, because the oracle tells me, well, your lasso estimate is going to have estimator is going to have the same distribution as the least squares estimator, using on only the relevant variables. So I'm just going to use that information from the least squares estimator. Now, in this figure, we see the results of our simulation exercise. So on my x-axis, I have beta 3 ranging from 0 to 2. So all of these points indicate one particular simulation experiment, and I vary this over many betas, so I can draw nice lines. On my y-axis, I have the coverage probability, which should be 95%, which is this line above here. So I've drawn this area green here, so everything between 95 and 1 would be good. Below you don't want, and certainly not a lot below. Now I have 4 methods that I do. I do first of all least squares, which is the black solid line. Note that this black solid line is steady here, close to 95%. It's not exact, but then again, I'm not doing an exact interval, it's only 50 observations. But it is not affected by the value of beta 3. I also do lasso in blue, I do adaptive lasso in red, and I do post lasso in green. So post lasso is where I first do lasso, I look at which variables were selected, and then I estimate a least squares regression only on those variables. Now, what we see is that for small values of beta 3, so beta 3, say below a half, a bit further below, say 0.3, 0.4, then the coverage probability drops dramatically. So we are saying that in those intervals, we say that in 95% of the cases, your interval should cover your true parameter. So your parameter should be in the interval. But actually it's 40% or even below 20%. So these intervals are really very poor. And it really needs beta to go up to say 0.5 here before those intervals start doing more or less what they should do. Now you might argue, of course, this is n is 50. So we have a very small sample, few observations. This is not really asymptotic. But still, I mean, these squares, which is hardly a super wonderful method, seems to do quite fine here. Our fancy methods, they screw up. So this seems to be worrying. Now let's look at when we increase the numbers to 20. Things don't get better, they clearly get worse. So least squares, suffering a bit from the fact the model becomes higher dimensional, drops a bit, but still remains unaffected by the value of beta 3. The other methods, they also drop. They do not get any better. So despite the fact that they should come into their own in high dimensions, they still suffer from very poor performance for small beta 3. This is actually very, very worrisome. Now let's have a look at an increase in correlations. So before I had a correlation of 0, now I had a correlation of 0.5. Well, it seems that the adaptive lasso is even doing worse now. It's really dropping very much. So maybe we were too hard on the method, so let's try something else, a different setup. And maybe this is more realistic and more in the way you would typically use a lasso. So let's assume that we're really interested in x1. So x1 is a variable of interest. I'm going to call it informally our treatment variable. So imagine we are doing a treatment effect analysis. We want to know what is the effect of the treatment x1 on y. But we know that we should include other variables. Otherwise, we cannot properly measure the treatment. So we know we should include some variables among x2 up to xp, but we don't know which one. So, well, there the lasso would be great. You would run it not penalizing x1 because we want to have that in our model anyways, but we do penalize all the other variables. And now we would do inference only on beta 1. So we would say, okay, this is the one we're interested in. We do inference on that, and we're depends on which variables on the lasso we actually include as well. So what I'm going to do now is to do inference on beta 1. Again, using the same principle, I use only the selected variables, and I use the oracle property to do least squares confidence interval on those. Now note that it's still beta 3 that I'm varying. So beta 1 is fixed at 2. Beta 3, the coefficient of x3 is the one that is varying, and the others are still fixed as they are. So I'm going to do the same methods again. Least squares, lasso, adaptive lasso, and post lasso. Alright, so this looks a lot better. So, well, thankfully our methods are not completely useless. So all methods, well, they suffer a bit, but then again, what do you expect with only 50 observations? But they're quite okay. They're not too far off. They're all above 90%. So, well, that's at least reassuring. So does it work in this setup? Does it mean that in this setup we can breathe and we don't have to worry? Well, let's do the same thing as before and increase the correlation to 0.5, from 0 to 0.5. That's not super dramatic, but it does start to get considerably worse already. And the lasso, well, it's starting to drop below 80% again. Now let's increase the number of variables to 20, from 10 to 20. Well, least squares suffers because there are now quite a lot of variables in your system. But the other methods also suffer. And the lasso goes towards 70% already. And well, even the others are also now dropping away from the 95%. So it still does not seem to be working that great. Now let's increase the correlation to 0.8. Well, suddenly it becomes again much worse. So the lasso drops, adaptive lasso drops, post lasso drops, and post lasso in fact only recovers for large beta 3. So there's something strange going on here. So we're doing inference on beta 1. We don't care at all about beta 3. But beta 3 does seem to affect how well our methods are performing. So there is something strange going on here, and as you can probably guess, it has to do with the fact that we do model selection first and inference afterwards. Well, one final confirmation, let's move from p equal to 10 to p equal to 20 to make things even worse than before. So one thing you might say, okay, we only did n is 50. Well, in fact, if you do a larger n, and I invite you to try it for yourself, you will observe very similar patterns. So increasing n, and I'll come back to that later, is not going to solve the problem, unless you make n really, really large. Now, there's something weird going on here that is not predicted by the oracle property, which is strange, because how can the oracle property not work? This was a mathematical result. People wrote proofs about this. So does it mean that the proofs are wrong? Well, no, yes and no. I mean, the proofs, there's nothing mathematically wrong with the proofs. What is wrong with the whole setup, the theoretical setup of the oracle property, is that actually, as we'll argue later, it's not the appropriate way to look at the problem. And what we need for that are tools of pointwise convergence and uniform convergence. And those will be the topic of the next video lecture. And of course, in a way, it also makes sense. And to me personally, it's also a relief, because it really did seem too good to be true. You would have 5,000 variables to choose from. You chose 10 of them which were relevant, and it did not have any effect on what you were doing. That seems really too good to be true. And once we look at pointwise and uniform convergence, we'll also have the machinery to show why this is indeed too good to be true.